So today we will continue our quantum journey and we will cover next topics. And up to this moment, we covered totally classical systems, and also we managed to speak about quantum basics, but mostly they were all around a single qubit. Of course, we have seen in general how do we define the quantum state for systems that can have also more than just two states, similarly for quantum transformations. But still, we were mostly playing around with a single qubit. And as we have seen, if we just have real valued amplitudes, we just have rotations and reflections on two-dimensional space that could, let's say, visualize our quantum system. Before we continue, I want first to remind you that today is the last day, so-called deadline, for the first homework. And what I have checked, I see that 39-40 people approximately have submitted their responses. There is one or two without enough points, so I hope that you will try again to get more points. But yes, please try your best today to finish the first homework so that then you can move on with remaining homeworks as well. We would like you to have a diploma at the end. Another thing, so that some of you won't run away too fast, I will again give you some 5 to 10 minutes break in the middle of our lecture, so roughly after 1 hour. And funny thing also, I had actually to update my Qiskit version because I kept getting similar errors also in other pages. So now I won't have those, but yes, I had to update Qiskit by myself as well. And last, when we will finish the lecture part, I will launch 2 more quizzes on the topics that we have discussed so far. So stay tuned, we'll have a bit more of this interactive fun that we had in previous lecture. I will start sharing the screen, and at some moment also I'll switch off the camera to save a bit traffic for better quality. While we didn't start with any specific topic, please let me know if you have any questions. Those can be on topics that we have covered or organizational questions. Maybe some life advices. I don't know. Quantum life, of course. Also, as usual, I will regularly check the chat, so I'll do my best to not miss anything. Let me see also microphone. I will admit one more person. And yes, sound should be fine. All right then. So for today, I also mentioned this in the schedule section of our Discord. We'll cover these 5 notebooks, and order will be a bit different from what we have here. Because sometimes these multiple control constructions can be considered as extra notebook because it's mostly technical part. So this is why it is placed after these 2, but it will be covered in our case before. We'll have enough time for those technical details. So if 1 qubit was fun, with more than 1 qubit, it can be even more fun. So this is why we will start with 2 qubits. And this is something that we have seen also in probabilistic systems, like what happens if we combine more than 1 bit into a system. So we can represent our states like this. For case of 2 qubits, our basis states are 0, 0, 0, 1, 1, 0, and 1, 1. And if we have state A, B, then we consider that we have first qubit in state A, second qubit in state B. Since we speak about basis states, then both A and B should be some value 0 or 1. And there are 2 more ways how we can write it. Like first subsystem is in state A and second in state B. This is what we meant when we have used tensor. And here, just if we write separatedly first qubit, second qubit together. This one about vector representation. So like vectors that represent our state. Here we can see that we have amplitude 1 for specific state and amplitude 0 for all others. Means that we have exactly concrete basis state. In this case, it is state 0, 0. So like a reminder that you can use these vectors as some entries that have some indices corresponding to the state to which they relate. So here we see state 0, 0 has amplitude 1, while state 1, 1 has amplitude 0 for this first vector. And a reminder from classical systems, it comes here. So when we are tensoring two vectors together, basically this is how we have obtained vectors for state 0, 0, 0, 1, and so on. So just by tensoring two vectors together, and here you can see in last column how this tensoring is calculated. So basically multiply each value of the first vector by whole second vector. And this is how we get the final values. So you see, like if we have two vectors, state 1 and state 1, tensor together, then we have vector in state 1, 1, and it is described by this column vector. And task 2 here is about generalization. So you can think about how it would look like if you have more than 2 qubits. Basically, then you would have a vector with 2 to the k dimensions. So like you have 2 to the k numbers here, and if you speak about the basis state, then corresponding entry will have value 1, while all other values will be 0. How do operators then would look like if we apply them for multiple qubits? So here, suppose that we have 2 qubits and we apply Hadamard to each of them. This is how our circuit would look like. This is something that you have already seen in the past. So circuit with 2 qubits, we apply Hadamard to qubit 0, and then we apply Hadamard to qubit 1. This is how it looks when we draw a circuit, and this is what is the matrix that we get. So here we, again, tensor, but this time we tensor matrices instead of vectors. It might look a bit more complicated, but principle, when we calculate it, is very similar. So basically, let me again do some drawing. We can divide this matrix in these 4 regions, and we get the first region by multiplying first entry from this matrix, multiplying by this matrix. And so then we get this portion of the matrix here. Basically, this describes what happens when our first system is in state 0. And so these are the transition entries for our matrix. And so you can guess that similarly, one by one, we can take each of the elements, do our multiplications, and so at the end, we'll get other entries of our matrix. So yes, this is how, from arithmetical perspective, it looks like. Yes? I guess I heard something. Maybe it was a glitch on my computer. So yeah, this is basically how we obtain this matrix. And now I will give you one more debugging tool. You remember from previous lecture, we had so-called state vector simulator. It is possible also to use unitary simulator. So maybe I will use some external source. So I will use Paint Online. And maybe we'll return back here again sometime later. So suppose that we have quantum circuit. We start in state 0 for all our qubits. I'll be lazy and draw just 2 of them. Then we have some operators applied. For example, we have Hadamard here and Hadamard here. And after that, we do some measurement. So we can apply measurement to each qubit. For example, this is like the most regular things that we were doing when building quantum circuits. So you remember that our QASM simulator would produce statistics from outputs of the measurement. So let's denote this QASM simulator. You remember we have been using state vector simulator. I will write it as STV, so state vector. So state vector was producing the final state of our quantum system that we would get before the measurement. You remember that it is possible also to do measurement and use state vector simulator, but this is more meaningless because then we will lose all our superposition information and we will get just some basis state like if we would perform just single experiment. So it is better to apply state vector simulator before the measurement, so you will get some extra information. You get all the amplitudes from them. You can calculate your probabilities, squares of their values. So therefore, you have even more information than just from regular statistics of the measurement. Now we speak about unitary simulator. And the thing is that each quantum operator, each quantum gate can be considered as a small unitary operator acting on a fixed number of qubits. So our Hadamard was acting on a single qubit. And we have sequence of such operators. In our example here, it is this sequence of operators. If we multiply all these matrices together, we can calculate some bigger matrix that just would mathematically mean the same computation as all this sequence of gates of our circuit. So in other words, this matrix could represent our circuit. And unitary simulator allows us just to calculate this matrix. And this can be useful as extra debugging tool. For example, if you define some quantum subroutine that you would like to use in multiple tasks or circuits, it might be useful just to first generate the circuit, apply unitary simulator, and so that you will get the whole description of the circuit, what it is doing. And I will show you what kind of information we can get from the very beginning. So here is example with our unitary backend, allows us to use unitary simulator. And here we use it for this circuit that we generated here. So to Hadamards, we applied it, and now we just execute unitary simulator. I think new version of Qiskit also will allow to do it in lazy way. So we can just print current unitary, and I think it still will be fine. It is not fine. All right, so it stopped working in new version. Oh, let's restart our kernel, because funny enough, it worked right after I have reinstalled Qiskit. So we'll launch this to Hadamards. Now we launch our unitary backend. And here we go. Now let me try also this. Yes, so now it works. You see, it is in not so organized way, but it contains the same information. The only difference is we have also J component here. It shows imaginary part of the complex number. 0 means that it has 0 value, so we have only real number part. J is denoting imaginary unit I. So you see we have 0.5 in real part plus 0 imaginary part. But basically you see it is the same matrix as here. Here we just can organize it in some specific way. Sometimes it might be more readable. But basically, as you see, this corresponds to the same matrix as we have computed here. So unitary simulator just calculated what would be the product of all our matrices. Since here they were applied to different qubits, it's just tensor product. If we would apply two different matrices to the same qubit in a row, then we would need to multiply them. So this allows us to skip some work of doing calculations. And so this is the final unitary that represents our circuit. And we can get some information from it. For example, if our initial state was 0, 0, 0, I mean, for both qubits, then this would be the final state that we would get. Similarly, all other columns can be analyzed in such a way. For example, we would get this final state if we would apply this matrix to the initial state 1, 1. To calculate it for superpositions, of course, you need to do carefully vector matrix multiplication. But you see, you calculated once this matrix, and now in your mathematical simulation, you could use just this matrix to calculate other possible outcomes. So this is a unitary simulator, and you see it gives even more information than our state vector simulator. Basically, in most cases, we will start with the initial state of qubits being in state 0, so that our final state of state vector simulator would be the same as first column of this unitary simulator. So in many cases, this one would give us more information. So in task 3, you're asked to define a quantum circuit where you have one Hadamard. So this circuit is already created. And now you would just asked to check how it would look in unitary simulator. So what kind of matrix do we get if we have Hadamard applied only to the first qubit? So now we have seen our matrix that we have generated, and this is how it looks if we apply two Hadamards to each of the qubits, and what will be the final operation. This is what we have calculated so far, and what would be the outcome. So here are three different ways how we can calculate it. The first one is straightforward, which most probably is used in a computer by default. So you do just like, yes. All right, so we have just straight vector matrix multiplication. We start in state 0, 0, which is represented by this vector. We applied matrix corresponding to two Hadamards. And at the end, we got exactly first column. We see all qubits have amplitude 1/2. Another way how to calculate it, we can separately apply Hadamard to first qubit, Hadamard to second qubit. So on first qubit, we get this state, 1 divided by square root of 2 for both entries. And for second qubit, we get similar state. And now we calculate what is the combined system vector. So we tensor two vectors together, we get this. The third way is just to write explicitly all the amplitudes. So if I apply Hadamard to state 0, we get the following state, 1 divided by square root of 2, 0, plus 1 divided by square root of 2, 1, exactly as here in the vector. Similarly for second qubit, and now we tensor them together in this way, as was described in classical systems. We put two basis states together, 0 and 0, and their amplitudes were multiplied. So we get 1/2 amplitude for state 0, 0. Similarly for all others. And if we write it in vector form, not a coincidence, we get the same vector. Because these are just three different ways how to calculate the same outcome. So then we get vector with same values. And in task 4, you were asked just to verify for some case for different initial state, how it is calculated. So for example, here, what happens if we start in state 1, 0? We will get completely different vector, but computing it in all three ways, we'll get the same final outcome, this one. So I hope all three ways of calculations make sense. And this is what you can play around in your spare time. But basically, yes, this is how we can describe mathematically how do operators acting on multiple qubits look like. So currently, up to this moment, we were using only single qubit operators acting on one qubit. Now we finally define operator that is defined for 2 qubits. And this operator is called C0. C0 means controlled node. So C control node is our operator. So if we look carefully at this operator, what we notice, what matrix do we have here? It exactly corresponds to node operator. And overall, what does this matrix mean? It is 2 qubit matrix, so 4 by 4. But this final part corresponds to the case when second qubit is in state 1. So this is how the effect can be described. It is a summary. For state 0, 0 and 0, 1 will not change. But for 1, 0 and 1, 1, the second qubit changes to the opposite state. So the principle is, if the state of the first qubit is 1, this is what defines our control, then NOT operator is applied to the second qubit. So this is why it is controlled NOT. If first qubit is in state 0, then control will not trigger, and therefore NOT operator is not applied, so that second qubit remains the same. So you can think of NOT operator being applied in a controlled way. How does it look in Qiskit? Again, as usually, it is a specific gate that is defined in Qiskit, CX gate. Now it will take 2 arguments because it is 2-qubit operator. First argument is our control qubit, controller, so one that applies this control. Second one is target qubit, the qubit that is affected by NOT operation. And here is the implementation, and we experiment by applying it to different initial states, 0, 0, 0, 1, 1, 0, and 1, 1. How do we get states 0, 1, 1, 0, and so on? We apply X gate to corresponding qubit so that we get 0, 1, 1, 0, or 1, 1. So here we define a loop for all 4 different cases. This part where we apply X gates to get the initial states that we're interested in, keep in mind that in this loop we create 4 separate circuits, and for each of them we'll do measurement, we display them, and also print the outputs. So you see, for the case when we had 0, 0, we applied C0, we did measurements, this is how our circuit looks like, and we get state 0, 0. Here for the state 1, 0, 1, we see also it didn't change. For state 1, 0, we obtained 1, 1, so control triggered. And similarly for the last case, 1, 1 became 1, 0. So again, control triggered on the second qubit, not operation, so 1 became state 0. I remind you, here we reversed bits because it was a nature of Qiskit where we first output qubit with higher index, then with smaller. So this is why here we applied X to Q1, and C0 goes from Q1 to Q0. You can see it also in the code. We apply CX from qubit 1 to qubit 0. Nobody is asking, but I guess when we started, we had a bit different notation. You remember here, we were defining quantum register, classical register. Then we defined our circuit by using this quantum and classical register. And here you remember we applied operator to some qubits from our register here. I wonder that nobody asked this, why here we use different notation. Here you can see we can do it in a bit shorter way. It has the same functionality. Maybe it would not allow you to access these registers in that straight way that was possible initially, but in order to create circuits and do computation, this allows us to have the same functionality, but in much more concise way. You can see that this way of writing is much smoother. So we just define how many qubits and classical bits we have, and then we apply just operators to specific index, knowing that it is qubits that we're working with. You might need to define quantum and classical registers separately if you want to have, for example, multiple registers, like separate entries in the same circuit. But in general, this approach also can be used. So you see we measured all our qubits and we start the outcome. Any questions so far? Yes, they're defined in a way that they're acting only on qubits, which are quantum bits, as you said. So basically, your circuit consists of qubits, and you are applying operators to the specific qubits. In your case, you apply X to one of the qubits, Hadamard to other qubit, and so on. So they're acting only on quantum bits. It is possible to have some similar classical operations like NOT operation, but in Qiskit here, these all are used only in terms of quantum bits. Here you don't need to clarify it. By default, this means that you have quantum circuit QC, apply operator X to qubit 0. So by default, it expects that it is qubit. And so here you just provided index. So there is no need to clarify that it was applied to qubit. Yes, you're welcome. So the last part of this notebook contains 5 tasks. I will not go through them. I mean, by showing you the code, this is what you would need to do after the lecture. But I will just shortly comment each of them, what it is all about. The first one, when you randomly pick pairs of qubits to apply CNOT operator, you apply it for 4 times, and then you need to check the diagram and try to guess what would be the final outcome. So it might be interesting because you might get sequence of CNOT gates applying to different qubits. And so as you remember, only when you have state 1, the target qubit will be changed. And then the changed qubit may affect the next one. And since it will be in state 0, then it will not trigger. So basically it is just to verify that you now feel comfortable by reading the CNOT gate acting on some qubits, how it is affecting our state. Another thing is that you need to randomly pick pairs of qubits, but keep in mind, if you try to apply CNOT operator where both qubits are the same, you will get error. Duplicate qubit arguments. CNOT gate only can act on 2 different qubits. This is something important to keep in mind. And this might be a mistake that you can make in task 5. So if in a random pair you would have pair of same qubits, then of course your circuit would not generate. So this is about task 5. In task 6, you will have to apply Hadamard to both qubits before and after CNOT. So basically what you will get would be a circuit where you have Hadamard applied to each of the qubits. Then you have CNOT applied in regular way. And after that, you have Hadamard applied to each of the qubits again. So this is a circuit that you're asked to construct, and then to see how it operates on 0, 0, 0, 1, 1, 0, and 1, 1. So surprisingly, by applying these Hadamard's before and after, you'll notice the same C0 effect, except that it will work in opposite direction. So it would be as if the control qubit became target qubit, and target qubit now is control qubit. So you can inverse the control operation by applying Hadamard's. Some of you may be wondering what's the point of such construction if we could just write C0 in opposite direction. And in a moment, I will explain you why it might be meaningful, not to mention that it shows very interesting quantum effect. In task 7, you're asked to apply C0 gate in very specific sequence. Basically, your circuit would look like this. You apply C0 in this direction, then you apply it in opposite way, like this, and then again you apply it back from top qubit to the bottom one. So this is our sequence of operators. And it will result in the following transformation. You see 0, 0, and 1, 1 will not change, but 0, 1, and 1, 0 will change to the opposite qubit values. Basically, this operator allows us to swap qubits. Amplitudes from first qubit will be transitions to amplitude to the second qubit, and also amplitudes of second qubit will be transitioned to amplitudes of first qubit. So swap operator, as if you would have two qubits and just exchange their places. So the question could be why these implementations can be important. And the thing is that C0 operator is very hard to implement on a hardware. And usually it can be the case that not all qubits are connected. So for example, here you can see topology of one of the first in cloud available IBM real quantum computers. So you can see we have just 5 qubits. And for example, qubit 4 and qubit 0 are not connected. In such case, you would need to apply swap operation to first get to the qubit 2 and then to the qubit Q0. Yes, it is correct commentary that in measure operation, we first write what is quantum bit that we work with, and second one, what is classical bit. And in most cases, we put the same ones. So yeah, this is how it looks. And also C0 operator can be implemented physically in many cases that it is acting only in one direction. So here you see on this diagram, from Q2, we can apply control node to Q4, but not in the opposite direction. Now we know how to apply it in opposite direction. We need to apply Hadamard's before and after C0 operator. This would allow us to reverse the effect. And if we would like to connect qubits that are not connected directly, we would need to swap qubits. So this is something to keep in mind, that we still can overcome hardware limitations because of the properties that we revealed in task 6 and 7. But keep in mind that this makes your circuit longer, which increases computation time and also increases the error accumulation on a quantum computer. And that's it for notebook about 2 qubits. Please let me know if you have more questions. All right. So in task 6, we noticed, will we have any part in the lectures about errors, fidelity, or results? No, it was not intended. So here we cover the basics of quantum programming. And by the way, this is a good point that we might need to have at least some talk or materials. In short, the current information that is given in these materials is only about that real quantum devices can have outcomes that are different from the perfect ones. But in general, it is complete separate topics that we need to cover in order to speak about errors, fidelity, and results. Not to mention that we need before that also to cover some more complicated topics. I think complex numbers in that case are needed to have more understanding about phase and then the introduced phase errors that are accumulated. Currently, just keep in mind that they accumulate errors and they are mentioned on their page usually when you consider quantum device. For example, it states what is error rate of some gates or measurement outcome. And then you can think of this as percentile, like each gate is getting you 1 more % of error probability. So this means if you have more than 50 gates, then you have more than 50% error, which means that your computation becomes unreliable. And answering this question about whether it is possible, yes, and this is the question which I can answer just by changing very few lines of code. So here we played around with Unitary Simulator, and we would like to have Hadamard and CNOT. Then it would look like this. So first, let's see what happens if we have just 4 Hadamards. Basically, we get identity gate. -0 is the same as 0, so it is just some calculational artifact, let's say, but it does not affect our outcome. And so here we can have CX gate. So you see now we have very simple simulator. So you can see these two elements are different and they will correspond to state 1, 1 becoming 1, 0 and 0, 1 becoming 1, 1. I guess here it might be because of the order. So if we write in this way, and here we get C not acting exactly on the opposite qubit now. Yes, it might be a bit problematic to get used to it because you remember the order of qubits. But the good thing, indeed, you can use such codes and just test in a straight way your matrices. All right, so what we observed here in task 6 is that if we apply Hadamard, gates before and after RC not was reversed. And here we'll speak a bit more about this phenomenon. So here we implement something similar to the task, but in a bit shortened form. So we start in state 0, 1 this time. After that, we need to apply Hadamard to both qubits, apply C0, and then apply Hadamard to both qubits again. So basically, it is what we did in task 6, but for one specific combination of states, for state 0, 1. So here we see how step by step, mathematically, these operations are described. So first we apply C0 operator. One qubit was in state 0, so we get this state. The second qubit was in state 1, so we get minus state. And composite system can be written like this. So we have first qubit in state 0 plus 1. The second qubit is in state 0 minus 1. We remember that C0 affects the qubit only if we have value 1. So that's why here we describe it. So again, before C0, we just rewrite this expression by open up the first bracket. So we have this first number tensor together with second qubit plus amplitude for state 1 from first qubit tensored again with second qubit. This is example where sometimes it might be useful to write all the amplitudes explicitly, because here we will see the effects of our C0 operation. So this is what we got. Now we apply C0 operator. What it does, if first qubit is in state 1, then for second qubit, we will apply not operator. So you see, this is before C0, this is after. What we can observe here in first part, nothing changed because first qubit is in state 0. Here, first qubit is in state 1, and we see 0 was replaced with 1, 1 was replaced with 0. So C0 worked here. So they're swapped in second qubit. Now what we do, we take out minus sign from here in front. So if we write the quantum state down qubit as of the down qubit, which is our second qubit, as before, the sign of state 1 in the up qubit should be flipped. So basically, you multiply this by -1, then you need also to multiply this by -1. So it is the same state, just written differently. And so this is the state that we got. And what do we observe? That before C0, we had the state here. And this will be the only difference here. Here we had plus sign, here we have minus sign. Notice that all other elements remained unchanged. What does it mean? We see that actually amplitude for the first qubit changed, but not for the second one. So after C0 operator, the sign changed to negative for the state 1 of the first qubit. So see, it was positive, it changed to negative. This is what I have marked here with green color. And this is what is called phase kickback. So now you have observed phase kickback effect. And this is the general reason why in task 6 we observed that we reversed the effect of C0 gate. So if we have this state, so we write back everything in brackets. So we put this here as both components are multiplied by the same. So this is our state after C0. So you see, before C0, this is state. After C0, this is the state. So only for the first qubit, we observed changes, although C0 was applied from first to second. And if I apply Hadamard to both qubits, now we'll observe state 1, 1. So as I mentioned, this is in more detail described case of task 6, but it is very important because it shows you the effect of phase kickback, how we can affect the qubit from which we apply C0. And phase kickback is very widely used in different quantum algorithms. In our case, we will observe it in Grover search tomorrow with the last lectures. But this is the effect of C0. And in task 2, you will have C0 applied from different qubits. But what is important, that qubit which is controlled, in this case it is Q0, is the one that has been in state 1 to which we applied Hadamard. So if we have state 1 and Hadamard, then the final state is this one, so-called minus state, as we remember it. So it turns out that phase kickback occurs when we try to control qubit in such state. Then such minus sign can affect the qubit that has been controlled. And we observe this effect better in task 2, because here we'll try to apply this control from different qubits, and we'll see that all of them will get this phase kickback effect. Remark why it is called phase kickback. Phase is this minus sign. We have discussed it a bit in quantum tomography. So we have local phase where we have minus between two qubit states, and we have global phase where it means minus outside the whole quantum system. So here we have local phase, and this is phase that is changed. We had plus, it became minus, so phase changed. And kickback because things that we tried to affect, but we got kicked back so that we were affected instead of us being the one who has affected. So just some play of words. But yes, this is mathematically how phase kickback looks like. And task 6 and tasks in this notebook just show us how this effect looks like. Please let me know if you have any questions. All right. Then I think we can continue. And this will be one more technical notebook. And after that one, we will have a break. Called multiple control constructions. So here we'll play around with more qubits and CNOT operators. You remember that how CNOT gate worked. And here we just show it in more appealing way. So like when we apply CNOT, NOT operator is applied to the target qubit if control qubit is in state 1. And this is the matrix that corresponds to such operator. So we see CNOT only when first qubit is in state 1. Is it possible to apply CNOT but only when control qubit is in state 0, but not in state 1? In other words, this is the operator that we would like to have. So we see now we would have CNOT only if first qubit is in state 0. So we want to change condition for our control. So in one extra classical notebook called operation notable bits, it was mentioned that NOT operator can be applied to control bit before CNOT and after CNOT to actually control in state 0. Why it works? Because you see, CNOT only triggers when first qubit is in state 1. This is the nature of CNOT operator. But if we applied NOT operator before CNOT gate, it means that CNOT only will trigger if initially our qubit was in state 0. Then it became from 0 to state 1, and then CNOT will trigger. And you see, if initially it was in state 1, then it will not trigger, as CNOT makes it state 0, and state 0 is not triggering CNOT. So this is the general idea of changing the control state to 0 instead of 1. At the end, we need to apply NOT operator to just return control qubit back to initial state. Because all we wanted to do, we wanted to apply CNOT to our second qubit, but we didn't want to change the first qubit. So you see, we applied NOT operator so that we changed the behavior of CNOT, and we apply NOT operator again to just return our qubit to initial state. So we can implement it in Qiskit. So here we see, again, I remind you that our indices go from largest number to smallest to work with Qiskit convention. So we apply X to the first qubit, then we apply CNOT from first and second qubit, and then we apply X again to the first qubit. And here is how our circuit looks like. And indeed, we got the matrix that we were speaking about. So CNOT is NOT operator, which is acting on second qubit if first qubit is in state 0. So it worked as we wished. This construction works. And by using this trick, more complex conditional operations can be performed. So this is also something that we may use in implementation of Grover search. So phase kickback and this one. So there exists also a qubit operator acting on 3 qubits, which is controlled NOT operator, CC-NOT in short, also well known as Toffoli gate. You can see here we even have Wikipedia link. Now we have controlled by 2 qubits. In Qiskit, it is very similar. You just need to provide 3 qubits as arguments. And the idea is that we have 2 control qubits, 1 target qubit, and again, control only triggers if both control qubits are in state 1. And it is again not operator that is controlled. And this is how the matrix looks like. So very similar idea. If both first and second qubit are in state 1, then third qubit will have not operator applied to it. And this is the matrix of CC not operator. And in tasks here, you're asked to also apply CC not, but now for different initial states. So you can think that CC not by default is applied from state 1, 1. But it can also be made that it will trigger, for example, from state 0, 0. So let me allow myself this time to solve partially this task for you. So this was C not applied for first qubit. Now let's see how it will look for CC not. By the way, here you can see we again use older way to write the code. So this is CC not, and we want to apply it from state 0, 0. And you can see exactly we got this matrix that is asked here. And you can play around similarly with different combination of applying and not applying not operators, and you can get the remaining matrices. So now we have C not, we have CC not, and we learned how to apply those not from state 1, 1, but making them trigger controlled not operator from some different states. For example, from 0, 0. The good thing is that we can scale it even to more control qubits. And here will be basic methods proposed. And it is possible also to scale it if needed. And maybe I need to restart this kernel. Ah, no, it already worked. So now we'll have CCC not. Such gate is not provided in Qiskit, except that at some moment they implemented a gate where we can provide arbitrary number of control qubits. But the thing is that our real quantum devices mostly will have just C not and some ways of CC not implementation. So still it is important to know like how this control scales for multiple qubits. In general, you can of course write just such operators like multiple control gates, and it will just get by compiling generated these CC not gates, Toffoli gates. But here also we can see how it can be performed by hands. You would need extra qubit for each additional control qubit if you work with Toffoli gates. So for example, here we want to apply control from qubit 3, 2, and 1 to qubit 0. With CC not gate, we can only apply control from 2 qubits. Since they just accumulate only if we have control qubits in state 1, then they would change target qubit to state 1. You can think of cascading it so that we'll have our additional auxiliary qubit in state 1 only if qubits 2 and 3 were in state 1. And after that, we apply control not from this additional qubit and qubit 1. And we see that it will trigger only if both of them are in state 1, and auxiliary 1 was in state 1 only if 2 and 3 were also in state 1. So therefore, this is how the construction look like if we want to apply control operator with CC not gates from 3 qubits. You see at the end we inverse this operation to return auxiliary qubit back to state 0. So here all 3 steps are described. By the way, here is example where we have to separate quantum registers. We have auxiliary qubit register and our regular quantum register on which we're working. So if we execute this circuit for different states of our initial qubits, then this is what we get. So you can see here no control has been applied. Last qubit didn't change, but for state 111, we can observe that indeed our target qubit has changed to the opposite state. So the remaining tasks are to play around with more qubits for control and also changing control qubits for state 0, not for state 1. So for example, here we have operator that we would like to apply control not only from state 1010, not from state 1111. So we would need to add some extra gates. But basically this task is extension for task 2, where we need to first cascade it to 4 qubits. And last task is that you can even define a function, so parameterize it, like here. So you could define any 4 qubit state from which you would like to control. So I highly recommend you to play around with these tasks when you will have time. It may be also a bit entertaining, like how to build more complicated constructions for multiple qubits. But yes, as I warned you, it is quite technical notebook. But here we use just 2 constructions. So first one is how to pass control to different initial states by applying X gates. And second, how to cascade CC0 operator to multiple qubits in order to implement control. So as I mentioned, programming languages may allow us to have such operators, but keep in mind that closer to hardware level, it will be reduced still to sequence of CC0 gates, which means that it is inevitable to have extra qubits. So it might be that your code won't compile that you applied control not from many qubits, but your quantum device doesn't have extra qubits to hold this extra auxiliary qubits. Let me know if you have any questions. I kept most interesting 2 notebooks after this, so don't worry if this one was a bit too technical. All right, then I propose to have a break, and it will be almost 10 minutes. So we will continue at 15:14. And until that moment, we will have this 10 minutes. If you can think about questions during this time, feel free to write them. And since I already announced, let me then answer this question after the break. I will explain because it might be also interesting to others to hear if they already left. So I will answer it after the break. Yes, no problem. See you all very soon. Let's continue. I guess, even more than 1 minute. And I hope that everyone arrived back. And there was a question which was asked right when I announced the break. So what was Toffoli contribution in quantum computing about reversible systems? Is there any special contribution in this matter? Toffoli gate, first of all, is a very important one because we have seen from these examples that it allows us to scale very well to bigger number of qubits. But what about reversibility? You can think of CNOT Toffoli gate or CC0 gate, this one. as reversible way to compute AND operator. So basically what we have, CC NOT gate is changing state of control qubit opposite one only if first two are in state one. And as we know, AND operator is equal to 1 only if both qubit bits are in state 1. So this is like you apply AND operator to first two qubits and store the outcome in the third qubit. And this is a reversible way how AND operation can be computed. And as we know, AND operator together with NOT operator form complete basis for logical Boolean circuits. And therefore, if you have Toffoli gate plus NOT operator, you in some sense have a complete basis for reversible classical computation. And of course, we can cheat a bit to apply control NOT can also replace just NOT operator if we use additional two qubits which are already initialized in state 1. Then in principle, Toffoli gate allows us to implement reversible classical computation by being universal one. This white state is a universal reversible logic gate. And yes, it is invented by Tommaso Toffoli. And okay, and it was mostly already designed when quantum algorithms have been implemented. And reversible gates have been studied in 1960s. So yeah, basically you can check the link for some additional information here. Yeah, you can think of Toffoli gate as being a reversible version of AND classical Boolean AND operator. And one more remark, Toffoli gate can be implemented with just CNOT gates and single qubit gates. Here, we would need complex numbers to explain this T gate and T dagger gate, but you can think about this picture in future by knowing that it is possible also to implement Toffoli gate by some 1 and 2 qubit gates. All right, so this is about Toffoli gate. Yes, you're welcome. Yes, here I mentioned T gate. We will not cover it in these lectures because it is gate that uses complex numbers. But what I can answer to you, it is that T gate repeated 4 times this as Z gate. So it is gates that can be considered as 4th degree root of Z gate. And as I said, it will contain complex amplitudes. Yes, you're welcome. This gate is covered in Silver course, by the way, where we discuss complex numbers. All right, so now let's transition to our most fun part, where we put our knowledge of using multiple qubits to some practice. So these last two notebooks and next lecture are about some algorithms, so something closer to practice. The first one is entanglement and superdense coding. And before I continue, you can think of these two protocols that we will discuss today as some, let's say, first steps in building quantum internet, because those can be very useful, and later I will also explain why. So here we describe two qubits. Let's say that we have two people, each of them holding one qubit. Asya has first qubit, Balvis has second. Both qubits are initially set to state 0. Now we'll speak about entanglement. Asya applies Hadamard to her qubit, and this is the state that will be. So her qubit has amplitude 1 divided by square root of 2 for both states, 0 and 1. So if we write this as combined system, this is the state that we get. We'll have, again, I will write indices. So for state 0, 0 will have amplitude 1 divided by square root of 2, and for state 1, 0. So basically, second qubit still remains in state 0. But after that, they apply CNOT operator on 2 qubits, where first one is control, second one is target. If we do calculations, this is the final vector that we obtain. So now we have 1 divided by square root of 2, 0, 0, plus 1, 1. And at this moment, their qubits are correlated to each other. What it means that if we do measurement by measuring both qubits, if first one is in state 0, this automatically means that second one also should be in state 0. If we measured first one in state 1, then we know for sure that second one also will be in state 1. This is something that we do not observe in classical systems, but quantumly indeed we can get entanglement that is acting also on distance. So this state here, experimental results has confirmed that this happens even if there is physical distance between two qubits. So if one of them secretly observes qubit by measuring, for example, Asa has measured her qubits, then Balvis will observe the same state if he measures, even if some times pass. He cannot observe the opposite state. So it looks like correlated quantum particles can affect each other instantly, as if they, even if they are on different parts of the universe. So if two qubits are correlated in this way, then we can say that they are entangled. So in some sense, they act as a one entity, despite the fact that they are by some distance. And so there is some technical note that if you have two qubits being entangled, it wouldn't be possible to write them as two separate systems. So in this example, before we applied CNOT, here we were able to write it as two separate systems. First one qubit is in superposition, second one in state 0. But after applying CNOT in this example, we got two entangled qubits, and it wouldn't be possible to write them in this way. So if two qubits are not correlated, we can mathematically write them as tensor of two qubits. If they are not, if they are entangled, then it is not possible. So entangled qubits can be useful. And most probably you can already guess that it is about some ways of communicating. So you see, if we would measure first qubit in state 0, then automatically the second one also is in state 0. So you can see that this would, in some sense, generate some secret information stored between these two people. So they are having some distance, and by measuring, you have equal probability of getting 0 or 1, but both people on distance would get the same state. So you see, it is not like communicating some very specific useful information to each other, but at least it allowed to generate the same random information for both of these parties. And there was no need to send to each other this information. They needed just to have this entangled qubit. But we'll see some other ways where this entanglement can be used for something more useful than just having random information. Let me know if you have any questions so far. There could be different correlations. Yes, for example, you could have, instead of 0, 0 and 1, 1, it is possible to generate state 0, 1 plus 1, 0, where always second qubit will be in opposite state. For other ways of correlation, you might need some a bit more tricky constructions, but these are just two examples that are easily definable. So how to generate this one? Before CNOT, you would just need to apply NOT operator to the second qubit. But Yes, overall, if you apply C0 from some superposition to the second one, there is some correlation being formed. And so you can play around with different initial state of the second qubit. So you may try maybe some other superposition. Then you will not have correlation like here where it is exact. Like one basis state will automatically correspond to a specific basis state on second qubit. There you would have some amplitude mixture or probabilities. But yes, there are different other ways to have correlation as well. These two are just simplest that come into mind, but are easy also to implement. So here our task is to send two classical bits of information by only sending one qubit. When you measure one qubit, you can get only state 0 or state 1. So in some sense, it is not possible to have more than one bit of information, at least deterministic one without probabilities from a single qubit. So if you have a qubit, you do measurement, you'll get one bit of information only. But here we want to have two classical bits of information by sending single qubit. And here how the circuit looks like. So we have IC and Balvis, and we make this entangled qubit. The same two operations that we have seen. We apply Hadamard and then C0. Now we have entangled pair of qubits. In order to entangle two qubits, they should be in the same spot. So they should be close to each other, so we are able to apply C0 operation. So now we have entangled our two qubits, and after that, IC and Balvis have some distance. So like they entangled their qubit and decided to communicate later. So Balvis go away. Now between IC and Balvis there is some distance. And then we want to encode two classical bits. So we have two classical bits A and B, and each of them can have value 0 or 1. So in total, there are four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. The protocol is the following. So IC has her qubit. She will apply Z gate if first bit that she's encoding is 1. If it is 0, then she will not apply Z gate. And then if second bit B is 1, she will apply X gate. And she will not apply if it is 0. So if her message is 0, 0, then she will not apply anything. For 1, 0, she will apply Z gate. For 0, 1, she will apply X gate. For 1, 1, she will apply first Z gate, then X gate. So here you see, we just draw it here as a control, like just to emphasize that it is conditioned. If bit has value 1, then the following operator will be applied. And so now the moment when this qubit is sent. So IC sends her qubit to Balvis, and Balvis needs to perform two operations and measurement. So he just applies C0 to both qubits, then Hadamard to IC's qubit, and then he measures his both qubits that he have received. And surprisingly, measurement outcome will be equal to the message that IC has sent. So he will get A in first qubit and B in the second one. So of course, here we had two qubits measured. But the good thing, through communication channel, we needed only to send one quantum bit, one qubit. And so this is what we get as the outcome. And this is the whole protocol. We can imitate it, of course, on our Qiskit simulator by playing around with all these operations. In reality, of course, we would be able to apply C0 operators only when qubits are together. So this is the moment when our qubit has been sent from IC to Balvis, and so he was applying this C0 operator. So this is the whole communication. Here it is also described as a text. I showed you partially. Then at the end, as I said, Balvis will apply C0 and Hadamard. Basically, you can see what Balvis does. He applies in the reverse order operations that were applied at the beginning. Hadamard and C0, now he applies C0 and Hadamard. Only at the end, he also does measurement. The measurement result will be exactly A and B. So here are mainly 4 tasks. Please do at least first 2. Other 2 can be considered as extra. Basically, we need to verify the correctness of protocol. So just to verify all 4 cases, to see that indeed sending 1 qubit is enough because we had this entangled pair of qubits. Initially, always our both qubits are in state 0. Then we apply Hadamard and CNOT. Then if A is 1, then we apply Z gate for first qubit. If B is 1, then we apply X gate to qubit, first qubit. And after that, we apply CNOT, Hadamard, and do measurement. And so just to see that indeed it will be the same as values of A and B. So this is a circuit basically that you're implementing in task 1. And in task 2, you're asked to verify on a paper. So try to follow what is the state of qubits after applying each of the operations, just to see that mathematically indeed it is correct. In task 3, you need to do it in reverse order. So suppose that again we have entangled pair of qubits, but now Balvis is the one who is sending message to Asa. And in task 4, the same task but on the paper. Idea of this extra task is to show you that if you have entangled pair of qubits, communication can work in both directions. So if Balvis will send message to Asa similarly, and she will do decoding in the same way, the outcome will be the same, so it will work. So if you have entangled pair of qubits, then super dense coding protocol is working in both directions. Why it is called super dense coding? Because we see it is indeed dense. We are storing coding, let's say, 2 classical bits of information in 1 qubit that we are sending. It can be useful if in some way we would be able to implement quantum channel of sending qubits as efficient as classical ones, then we could increase throughput twice by this super dense coding. But also it is good for security because the only information that is sent is a single qubit, and it will not be able to reveal information of both bits that have been encoded. Basically, the measurement outcome would be some random bit value, but we cannot reveal outcome of the second bit, definitely. And this is the super dense coding protocol. Let me know if you have any questions. Just for fun, I will Google something, super dense coding. So here is quite similar diagram. And here is the security of it. It's possible to have more general scheme. And there are experiments to improve it. So it is even possible to surpass 2 bits information per particle sent, like not exactly qubits. But yes, this is something to play around with. But even this one was already improvement in 2004. You have fidelity 0.85 with capacity of 116. So overall, channel effectiveness could be a bit bigger than 1 bit information per particle. And this was already better, so we had a bit better fidelity and also much better capacity. So yeah, it is possible to improve it. If we speak about sending, like using it as a channel, you can have just multiple pairs of entangled qubits, and for each pair you apply this protocol separately. This is how quantum communication can look like. All right, since I didn't observe any questions, I assume that we can check the last topic, which is called quantum teleportation.
Quantum computation governor. Certificate of course. Duda certificate la apply kara quantum information.
All right, I assume it was not a question. And so here we have quantum teleportation. It is advised to use blank paper, at least one, in order to draw the circuit of protocol step by step. And also there will be some tasks that would require calculation, similarly, like we had with super dense coding, to see how it all evolves mathematically. So in super dense coding, we wanted to send 2 classical bits of information by only sending 1 qubit. Here what we will do, we will teleport a qubit by sending 2 classical bits of information. So first, some discussion. We can have arbitrary quantum state here. So basically these are 2 amplitudes, A and B. Both of them in our case are real numbers. We can generate it by applying, for example, rotation gate to our qubit set in state 0. So we have some qubit in state V. If ISA would be able to have multiple copies of this qubit, she would be able to collect statistics based on these qubits and obtain approximation. So these are our measurement outcomes, you remember, how we did quantum tomography, for example. You had like 100 or 1,000, you had 1,000 qubits in the same state. You did measurements, and so you obtained some statistics, so you could evaluate amplitudes of A and B by estimating your rotation angle. So ISA then can send her estimate by classical bits. The number would depend on precision. But we can do better. If we have entangled pair of qubits in advance, it is possible to recreate state of ISA's qubit after receiving just 2 classical bits of information from ISA. So ISA has 1 qubit. She will use this entangled pair of qubits, and then Balvis would need to apply some operation, and at the end he will have exactly same qubits that ISA had before. And here is the protocol. So we work with 3 qubits this time. ISA will have your quantum message, key, let's say. So she has qubit Q2, which will be in some state, A0 plus B1, so amplitudes A and B. This is qubit Q2. We can have entangled pair of qubits, Q1 and Q0, which will be in state 1 divided by square root of 2, 0, 0 plus 1, 1. So you see, ISA already has her qubit in state V. So we can assume that it is already in state V, so we don't need to initialize it. These 2 are in state 0, so we need to entangle them. So we apply Hadamard, and then we apply CNOT. So this is the preparation before actually using our protocol. So you see, beginning is similar to what we had in super dense coding. We need to first have entangled pair of qubits. After that, ISA and Balvis are on some distance. This is the quantum state of our system. So ISA can prepare her qubit in state V also after Balvis has left. So they have entangled pair of qubits, then ISA prepared this state V, and now she wants to send it. So this is the system that we will have. First qubit is in state A0 plus B1. Next 2 qubits are entangled. And if we write it as a combined system, this is how it looks. 1 divided by square root of 2, amplitude of A 0, 0 plus A 0, 1, 1 plus B 1, 0 plus B 1, 1, 1. Now ISA applies C0 operator between first qubit and second qubit. So both qubits that she has, Q2 and Q1. She needs to apply C0 operator. And we need to calculate what will be the outcome. Since she applies C0 to her qubits, first and second one, we'll see that here nothing will change. Here we have state 1 in her control qubit. So this is where we will get where it was, this one. Oops. Here she will have now state 1, 1, 0. And here she will have state 1, 0, 1. So this is the only change that would be after applying C0 gate. Because we were working with first two qubits, applying C0 to them. This is the state that we'll have. So only last two base states will change. After that, ISA applies Hadamard. So later, I recommend you to check this task to convince yourself. Try to do it on paper, and later you can see also in the solution how it is calculated. So we start in this state after C0, we apply Hadamard, and here how it is calculated. So when we calculate it, what we observe? We observe that amplitudes A and B has been moved to the third qubit instead of the first qubit. So it turns out by applying C0 and Hadamard, we were able to pass amplitudes from first qubit to the last one, to third one. We see there is some difference, of course. Here we have plus, here we have 0 and 1 switched places, here we have minus. But what if we have this system and ISA would do the measurement? When ISA measures first qubits, and remind that these are first two qubits, then we see we have 0, 0, 0, 1, 1, 0, and 1, 1 with equal amplitudes, 1 divided by 2. So it means that she will observe one of these base states with equal probabilities. 1 over 4 is this probability. Depending on the measurement outcomes, then the last qubit, because of the entanglement, will be in corresponding state. So if we observed here 0, 0, then last qubit will be in state A0 plus B1. If, for example, we measured 1, 0, then last qubit will collapse to state A1 minus or A0 minus B1. And this is what is described here. So depending on measurement outcomes, Wallis qubit will be in the following state. So by doing measurement, we collapse our system in a way that now we know what can be the state of our final qubit. So amplitudes of A and B has been transformed to Wallis. But we need now to send classical bits of information. So if ISA sends a measurement outcome, then Wallis can reconstruct exactly. And what it was A0 plus B1. So as we see, if measurement outcome was 0, 0, then Wallis will have his state already the correct one. And in task 3, you're asked to see what gates do we need to apply to Wallis qubit by knowing the classical bits of information. So here we have all 4 cases. So suppose that Wallis receives classical bits 1, 0. Then it means that his qubit is in state A0 minus B1. But we should get state A0 plus B1. What is the gates that we should apply to this qubit in order to get exactly the state of the qubit that we need? So what was the gate in this case? So we received measurement outcome 1, 0, and we know that our state is 1, 0 minus B1. No, we want to... So I will write here. Suppose that we have measured So idea here is that for all 4 cases, there exists some gates that you can apply to it in order to recreate the correct state. So when we did measurement, our last qubit has been changed to some of the states. And here we have 4 different cases. They only depend on classical measurement. So we see if we received 0, 0, it means we already have qubit in correct state. But each of these 4 outcomes can be with equal probability. So we might get different outcome. If we get 0, 1, then according to this, we can see that our qubit will be in state A0, A1 plus B0. So we would need to apply one more operation. Balvis cannot see his exact state, but by this classical outcome, he knows how the state has been changed. So he needs to compensate this change by applying one more gate. So he wants from this one, A0 minus B1, to get A0 plus B1. He needs to apply one gate. What is the gate that he needs to apply? All right, I will write the answer. In this case, we need to apply the gate because it multiplies amplitude of state 1 by -1. For the second case, if we received amplitude measurement outcome 0, 1, then we need to apply some different gate. But basically, idea is that you need to return the state of the qubit to the state that was initially sent. So ISA has this state. And at the end, Balvis should have this state. But he gets one of the 4 possibilities. But by having classical bits, he knows exactly what it is the possibility. So if he gets 0, 0, he knows that it didn't change. If he gets 0, 1s, he knows that amplitudes for state 0 and 1 has been exchanged. For 1, 0, he will know that amplitude for state 1 was multiplied by -1. And if he got 1, 1 classical bits, then he knows that both bits have been exchanged and also multiplied by -1, the amplitude for state 0. So here he would need to apply different gates depending on what were here. And so, yes, sure, no problem. It is recorded, so you can check what left. Actually, we almost finished, by the way, and soon we will have a quiz. But thank you for joining. So yeah, later you can check also solution of task 3. If you are not convinced that this operator will work. But as you can see, we start in the following state. We apply C0 and Hadamard, and then our amplitude from first qubit is teleported to the last qubit. So in terms of quantum teleportation, amplitudes have been teleported from one qubit to another. They were not copied, they were not sent, they just teleported. And by knowing the measurement outcomes, we can recreate the state in the third qubit exactly, so that it corresponds to initial state of Asa's first qubit. And in task 4, you would need to implement this circuit and check the state vector simulator to see that indeed the amplitudes from first qubit have been transmissioned to the last qubit. And in task 5, you can also use these intermediate measurement outcomes so that you would be able to apply controlled operations depending on the classical outcome. So that instead of recreating the state by applying X and Z gates, you would just take classical bits and apply control version of gates. So task 5 shows exactly how we would implement it in practice, this protocol. In current case, we would just get our qubit, and after that, we would apply operator by checking the classical bits. This is like more automated way how to do it. And let me show you, this is a circuit that we would have as a classical teleportation, I hope. Yeah, it should be good. So here we would have Asa having her qubit in state X. We have entangled pair of qubits. We apply here C0 and Hadamard, and then we would have measurement and we would apply X and Z gate in order to compensate the changes, and at the end we would have exactly qubit in state X on the third one instead of the first one. So this is the circuit that implements quantum teleportation, and this is what you are asked to do in task 4. And yes, here are some formula descriptions about how it worked. Please let me know if you have any questions or comments. While you're thinking or typing questions, yes, it is fine. And if you will have questions at any moment, you can ask them either in Discord or now or tomorrow in the beginning of lecture. So no worries if you need time. These sections will take a bit of time. But before finishing about exactly this notebook, I would like to... Is there a way? Okay, I can just press new. So I would like to show you what is the idea of using this protocol, because it allows to securely send any information. So Isa's qubit can be also initialized in some classical state. So she can just have 0 or 1. And she can secretly send it to Balvis. So for example, she's here on top of the mountain. Here we have some lake. Here we have Balvis. Initially, they have entangled their protocol, their qubits, and then Asa created her qubit in some state. She applied the operator that she needed, and then she can even broadcast these two classical bits of information, for example, 0, 1. And everyone here, by getting these bits of information, they will not understand what this information means, because as we have seen from the protocol, Asa measures her qubits, and each of the basis states have equal probability, 1/4. So basically, these are just two random bits, but these two random bits are affecting computation in predictable way. So Balvis knows what he needs to do. This is what is described in task 3 here, to recreate the state of his qubit so that he will get exactly state that ICO has been sending to him. So this is very secure communication protocol, and some secret information can be sent. So no mystical creatures can any bits of this information. So quantum teleportation can be used for secure sending of any messages. In this way, you are sending quantum messages. Classical bits do not depend on this quantum information. They are totally random. And so we can recreate multiple qubits of information by this secure communication protocol. If somebody will make an NFT from my drawings, let me know. It will be fun. So that's it that I wanted to show you today. And as I see, some of you would need some time to think more about, especially this one, quantum teleportation part. But basically, as you see, it's mathematics that is affecting it. And at the end, the measurement outcome allows us to recreate the final state. I will give you some 2 more minutes if you generate any questions. If not, please feel free to ask them on Discord and also tomorrow in the lecture. And after some 2 minutes, I will start the quiz. So I will write it in a moment. I'll also stop sharing for a while. Well, it's not exactly about predicting quantum outcome. It is more about that if we know these classical bits, so yes, they are probabilistic random, but they are related to what is the final state of that Balvis qubit. And he can recreate initial ISO state. So he still will have unmeasured qubit in state A0 plus B1. So basically, classical bits allow us to recreate this state. And these classical bits are needed to apply last operation so that from arbitrary case of these 4, you can get the correct one, which is this. But in some sense, yes, you have predicted how the qubit has been affected. In this sense, it is predicting the quantum outcome. But the good thing is that you receive unchanged qubit, and at the end you can either do measurement or you can even do some more computation. So quantum teleportation could be used also for some distributed computational protocols if needed. Clusters of quantum computers. Let's see if it is our future. So now I will share the screen where we have quiz, and I will launch it in a few seconds. So next share is quiz channel. And I'm launching quiz in a few moments. I hope that all the quizzes are working. So I need to apply play command and quiz number. So 5 seconds and we're starting. And good luck, everyone. Here we go. Okay, so we have 18 participants and we have quite good result. So well played. Nice. And after a few moments, we'll start the second quiz, and it will be more about the protocols that we have discussed so far. So I understand that some of the stuff still might be not 100% clear at this moment. But for that, also feel free to later ask questions. And now we will launch our quiz for these communication protocols. And here we go. By the way, this is example where you can see different correlations between qubits, because here only one of them is not entangled, so other three are the ones that are working out as entangled. Well, I guess leader didn't change. Oh, actually changed. That was very close. I thought Pafonso will be the first one, and then he was outrun. That was very close. So the last question was decisive one. So this is good. Nice results. But yeah, we have clear leader for both quizzes. All right, that's it then for today. I think we can stop also the recording.